All right, so elimination mechanism. So we want to talk about specifically E2 today. Um, Now, let me draw out this generic alkane with X as the leaving group or halogen, and then we have a beta hydrogen sticking up there in blue. And I'll highlight this X in red, that leaving group. So the base comes in, we form that pi bond, we kick out the X. Now we create this alkene here with the different R groups on there, right? So is this process going to be a one-step or two process or a two-step process? It's very, 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 very similar to SN1 versus SN2, right? So an E2 mechanism, which is what we're going to be talking about in this video, is a bimolecular elimination, meaning that, and then there's a E1 mechanism, which is a unimolecular elimination. So bimolecular elimination, meaning there's two species involved in the transition state or the rate determining step, however you want to look at it. And so let's take a look at the like, I don't want to say stats, but the criteria for E2 mechanism. All right, so for the kinetics of an E2 mechanism, we already know a lot of this stuff. So it's an E2 mechanism, so it's second order. It's bimolecular, and so that means it's a one-step process. And it looks exactly like the kind of the mechanism we did above, where we just draw the arrows and go bang, bang, bang to the product, right? So rate is equal to K times the alkyl halide times the base, the concentration of the alkyl halide in the base, okay? So let's go ahead and draw out our a generic alkyl halide, and we swoop on that beta hydrogen with a strong base like hydroxide, and that forms that pi bond and kicks out the leaving group, okay? So I guess just to highlight the hydrogen in blue and the leaving group in red, I kind of want to just show you where those electrons end up, and that is here as that pi bond, okay? So we also end up with water as well as bromide ion for a byproduct. So let's take a look at the energy diagram for this. It is, again, since it's bimolecular, it's a one-step process. It's going to look just like the SN2 energy diagram. So we've got one hump, and we have the alkyl halide on the left side as well as our hydroxide, and then we've got our alkene product plus water and bromide, etc. So this, again, this looks exactly like a substitution reaction, right? So remember, one step equals one hump in the energy diagram. Okay, so remember on the top is our transition state indicated by this double dagger. So let me draw that transition state for you because it's really important that we understand what it looks like to understand future concepts. So we've got our two methyl groups sticking up. We got our bromine here. Remember, that bromine bond is being broken, so that means we have to draw that with a dotted line. And then we're breaking the hydrogen bond, carbon-hydrogen bond, and then forming a pi bond and also an oxygen-hydrogen bond. So that's why those are all dotted lines. We have delta negatives on the bromine and the oxygen because they are negative, i.e. the OH, or they will become negative, the bromide. Okay, and that's the transition state. We're partially forming the alkene product, right? And so if we're looking at the energy diagram and the products in the end, we have two things breaking down into three things. And so that's increase in entropy. So this reaction is entropically favored. And so this is just it is also in this case exothermic. And so we have that in our favor as well. And but we just kind of want to point out the idea of entropy and how we can favor a reaction with entropy as well. Okay. So just like the SN2 and SN1 reaction, we had these four factors, right? We had the alkyl halide, the base, the leaving group, and the solvent. And we wanted to take a look at each of these to decide if it what type of mechanism it was, right? So let's lay out the criteria for an E2 mechanism. Let's start with the base rather than the alkyl halide because there's much to say about that alkyl halide. Okay, so let's the base first and foremost. Okay, as we've mentioned a few times, remember the base is we want that to be non-nucleophilic, super strong, right? And for this rate equation, we do have the base in the equation, so the concentration of the base does matter, and so its effectiveness does matter. And so again, we want a non-nucleophilic base, if for the best possible outcome. And one of the bases we already pointed out was this tert-butoxide, the chicken foot, right? We can also write it as OTBU. Now there's a couple other non-nucleophilic bases that I want to introduce, and so that's this guy right here with the two nitrogens, DBN. And then we also have a very similar structure for DBU, another base that's non-nucleophilic. It's non-nucleophilic because it's so big, right? It's so bulky. You can't really attach onto a carbon and just stay there and have it be stable. So I also just want to point out that the nitrogen on the right is the one that does all the attacking, and you can think about that because of the imagine it grabbing a proton and then being resonance stabilized. So just keep that in mind because that's a great question to ask. So we have for DBN, it's called DBN because it's 1,5-diaza bicyclo 430 nonene. Okay, so that's a mouthful, so we're just going to call that DBN, right? I do want to point it out though, obviously the DB and the N are capitalized in here to show you where that name came from. And then DBU, very similar again, but it's 1,8-diaza bicyclo. Now it's 5,4,0, and the last part is undecane, or decene. And so there you go. That's the DBU. These are two options for non-nucleophilic bases. So if you ever see these, you're gonna think, okay, it's if you see tert-butoxide or DBN or DBU, then you're thinking elimination reaction. Okay. Now the leaving group, of course, we want a good leaving group, which is a weak base, and that's going to increase the rate of an E2 reaction. Okay. So solvent, we also want a polar aprotic solvent, right? Just like SN2, we wanted polar aprotic. For E2, we also want polar aprotic because it doesn't solvate the anions, right? And so if we're using negatively charged bases like tert-butoxide or hydroxide, if they're not solvated well, then it's just a naked negative charge and it's highly reactive. And so very much just wants to swoop on a proton to stabilize that charge. Okay, so again, if the base is more reactive, then the rate of the reaction is going to be faster. Okay, let's talk about that alkyl halide now, because there's much to say, much to do. So the identity of the alkyl halide, first and foremost. All right, so first and foremost, you can't have a methyl halide, like an alkyl halide, and then have an elimination reaction. Remember, you need at least a primary, right, to form that carbon-carbon double bond. Okay, so that's why we don't have that in this chart. We have a primary, secondary, and tertiary alkyl halide. Been seeing this before. Okay, so nothing new here. However, we do want to talk about the increase in the rate of reactivity for E2 as well as SN2. Okay, so let me just draw my trusty little arrow here. All right. Okay, well, it doesn't want to make a triangle automatically for me. Rawr. Technology. All right. Let's try again. Sorry. I really want this triangle to just automatically be made so it doesn't look all wonky. Anyway, I give up. Increased rate of SN2 reactivity as we go from right to left. Remember, because of sterics, we wanted backside attacks, so the primary was going to be faster than the tertiary. But check this out. Oh, got them first try. I think I needed to not overlap those lines. So, uh, increased rate of reactivity for an E2 as we go from left to right. Okay, so that's primary, secondary, tertiary. Tertiary is going to be more reactive than a primary for an E2 mechanism. Okay, so what you talking about, Jess? Why is that? Well, that's because we have an increased number of R groups on that tertiary alkyl halide. Okay, so um, again, we could talk a little bit more about this, but let's draw an energy diagram here for you. That's gorgeous, right? So we got that transition state on the top, right? So remember what the transition state looked like. We had a partial double bond being formed, and then obviously the partial breakage of that hydrogen carbon hydrogen bond, partial formation with the BH bond, and then partial breakage of the CX bond. Okay, so this is our transition state. Now, what's important about this transition state is that we can see that we have the formation of that alkene forming. Okay, so remember, if we can increase the stability of the transition state, then we can increase the stability, in this case, of the reactants. But in the end, it's all about activation energy being lowered anyway, right? So the more R groups stabilizes the alkene, right? We've already talked about that. And then if we can stabilize the alkene, then we can stabilize the transition state, and then we can also stabilize or lower the activation energy, which in turn increases the rate of the reaction. So that's all she wrote, folks. And boom goes the dynamite. The crowd goes wild. Okay, well, that's the explanation anyway. So maybe it wasn't super exciting, but I liked it. So we have to talk about practice. All right, so let's do a little bit of practice, and really, it's pretty straightforward stuff. I think again, if you handled that chapter 6 and 7, I think you're gonna kill this chapter. You're gonna be cruising. It does get a little bit weird when we're starting to compare substitution and elimination, though. So just get ready. Rank in the order of increasing E2 reactivity. Okay, so what I want to do is kind of just go. I want you to draw the products. Okay, so because I know you can just look at what it is, but I want you to draw the products. Okay, so we got this alkene here for this product, or the product of this one right here is going to be that alkene as well as this alkene. We've actually seen that before. There's both of those. And then for this alkyl halide, we have this alkene, or we have this alkene. Okay, and so the reason why I want you to draw these products out is obviously to get the practice in that, but just to kind of show you that, or show you what the product's stability will be, because you can look at an alkene and say, hey, that's the more stable or not, and then you can work your way back and say, okay, well, that's the fastest reaction because we form the more stable product. So working from the top to the bottom, we got a mono-substituted. One of the products is a tri-substituted in the middle, and then di-substitute for the bottom. So we can rank according to number 1 being the middle, number 2 being the bottom, number 3 being the top, because of the product form. More substituted, tri, is number 1, more stable, and so it's faster reaction. Well, mono-substituted is higher in energy, and so the reaction is slower. Okay, so let's take a look at number 1. We have 2 totally different products being formed, right? And so we have a di substituted as well as a tri substituted. At least on the bottom, there's 2, but they're both di substituted. So let's focus on this one here, where we're getting a di substituted versus a tri substituted, and let's talk about basically which one's gonna, or basically how the outcome is going to look. Is it going to be equal amounts, or we're going to get more or less of the other one? And so that leads us to Zaitsev rule. All right, so the definition of Zaitsev's rule, it's basically named after the Russian chemist who figured it out, but it's the major product is the more substituted alkene. Okay, Not too difficult, right? So that means that the major product in this case is going to be the tri-substituted. Okay, so what we would do is we draw both products, typically identify that as the major, and this one as the minor. And then we move on. Next problem. All right, so that leads us to the concept regioselectivity. And regioselectivity is a reaction that yields predominantly one constitutional isomer. And this is obviously when there's actually more than one possibility, and so otherwise it's not considered selective. And so yes, in this one right here would be a regioselective example, and that's because E2 in general is regioselective. If we have the possibility of forming two different alkenes, then you're going to favor the more substituted one, and that's the definition of regioselectivity. We also have the idea of stereoselectivity. So a stereoselective reaction is one that yields predominantly one stereoisomer. So typically this is going to be like a cis or trans, and that's obviously when two or more are possible. Okay, just like before. I feel the need to change the color of this. Let's make it pretty and pink. Now let's also go over an example of what I mean by that. So in this particular case, we have this alkyl halide, and when we throw ethoxide in there, like in the form of sodium ethoxide, or you might see it as Na plus O minus CH2CH3, however you see it. It's a strong base as well as a good nucleophile, but in this case we're going to use it as a base. To remove that proton and form the alkene, we can form this alkene here, and I'll go ahead and abbreviate the benzene ring as a phenyl group, as a pH. So we form two isomers, cis and trans. Trans is going to be the major isomer, and the cis is going to be the minor isomer because of sterics, right? It's less stable, and so therefore this reaction is stereoselective as well, and this reaction is an E2 reaction. So write it down. Let's see. Look at this puppy. Come on now. Look how cute that is. You know how long it took him to catch that ball? He had to do a lot of what? A lot of practice. All right, so let's get a practice problem in or two and see what comes of it. So we're going to be masters of E2, SN1, SN2, E2, and E1. All right, so what we want to do is decide what the major and minor products are going to be for each of these alkyl halides. Okay, so I'm going to draw some out. I encourage you to pause the video and then write your answers down and see if you get the same thing that I get. If you disagree, if you have some sort of discrepancy with the answer, of course, just reach out to me. But we got this alpha carbon here, the beta carbon here, therefore the beta hydrogen is on there. We also have another beta hydrogen, okay? So that means we're going to have a couple different products here. So let me draw this gorgeous arrow. All them right angles, you know what I mean? So I'm just going to abbreviate it as like the loss of, you know what? H1, that's actually a terrible example of I'm gonna change the H1, H2 to, I gotta change it to like A and B, because H subscript 2 looks like H2Br, like there's two hydrogens, so my bad. All right, HA and HB. Base comes along, removes that HA, and then we get an alkene product right there on the left side. We could also get this one, but those are the same. If you go ahead and, the reason why they're the same is because these two groups right here are the same. Okay, if you flip it over, same exact product, no difference. We don't have like a cis or trans or E or Z in this case. So if we remove the HB proton, we will definitely get a different compound. And so we can, in fact, get a cis or trans product in this one as well. And so here you go. here are the two products. We got cis here and we got trans here. Okay, so if we wanted to identify major and minor, so trans, yes, major when it comes to trans and cis, but the compound on the top of the overall reaction is the major product, and that's because it is tri-substituted. Okay, and plus, statistically speaking, those two are the same on the top. And then, but we will get more trans than we will of cis as those minor products. Okay, so we got a minor product and then we got a minor product. All right, so let's take a look at this other alkyl halide. Let me go ahead and move these down here, so that way we can we got more room. Okay, so we want to identify all of our beta hydrogens. So we got beta HA, HB, and HC. So what we're gonna do is draw at least 3 products here. Okay, so let me just give you 3 nice right angles. All right, so we got a cyclopentane, and then we're going to remove HA first, then we're going to remove HB, and then we're going to remove HC. So let's go ahead and jump to these products. We got an alkene where that methyl was, and then for the removal of HB, we've got an alkene on that side. Oh, I forgot the methyls, my bad. And then we got an alkene right here. So that's a nice little tetrasubstituted alkene. So let's classify all these. We got di, tri, and tetrasubstituted. And so if we're going to classify our major and minor, the tetra is going to be the major, and the di and tri are technically both minor because they are formed in lesser amounts than the tetrasubstituted alkene. So let's take a look at this alkyl halide right here. We've got 2 different locations that we can remove a beta hydrogen, and then we can also form a cis and trans alkene for that compound on the right. Okay, so in this case, we have a cis and trans isomer. We also have a mono-substituted isomer. They're both di-substituted on the right, but that means that the major is the trans isomer on the right because trans alkenes are more stable than the cis due to sterics. So this last one right here, it is a secondary alkyl halide. And this one's a good one, so I really want you to focus on this one because we have a beta hydrogen on the left, but we do not have a beta hydrogen on the right, or like below that alkyl chloride. Okay, so that's because it's a tetra substitute, or it's a quaternary carbon right there, and there's 4 bonds to it already, no hydrogens on there, and so this is the major product as well as the only product. Really important that we can identify this. If we created a carbon-carbon double bond there, then we would have 5 bonds. So that's definitely going to be asked. All right, so for stereochemistry of the E2 reaction, this is really important. I told you we would get to this, and here's this one right here. We do form that product, right? We saw that just above in a similar manner. We had cyclopentane, but in this case we have a cyclohexane, right? So not too much has changed there. That's cool, right? But let's say we have this particular stereochemistry. We'll still get this product, right? Yay, we still get the product. But, and I mean a big dirty dog butt rubbing on your carpet butt, I don't know, that cracks me up. Dogs rubbing their butt like that, that's like literally the best thing in the world. Besides my kids and my wife. So, thank you. Let's say we have this stereochemistry where there's an inversion about that upper carbon. That E2 reaction does not occur. It does not occur. We get no reaction. Like, what you talking about, Jess? Is that a typo? No, it was not a typo. I would have edited that out. Probably not. I would have left it in there and I would have just told you that was a typo. Ain't nobody got time for editing. Okay, so long story short, the orbitals for the proton and the leaving group need to be parallel to one another. So there's basically two different options. We can have them both pointed up in the same plane, where the dihedral angle is 0 degrees. Okay, remember dihedral angles from chapter 4, maybe? Well, this particular orientation is called syn-periplanar. Okay, so again, those orbitals are still parallel to one another, but they're pointed in the same direction. We also have another scenario where it could be completely opposite of one another, still in the same plane though. Okay, so they same plane, they are parallel with one another. That's where periplanar comes from. But one is up and one is down, and so this is going to give us a dihedral angle of 180 degrees. And in addition to that, the name of this orientation is called anti-periplanar. So you can think of it as like anti as in anti-conformation for like a Newman projection, right? So this one up here on the left side, is eclipsed, and then obviously the anti conformation is going to be lower in energy, and the eclipse is going to be higher in energy. So that kind of leans us towards preference of the lower energy conformation for this particular reaction. For this particular mechanism of this reaction. And so E2 most often occurs in the anti-periplanar position. Okay, so and that's because just by looking at it in terms of anti, it is a lower energy conformation, and so this is going to allow the reaction to move forward much easier, right? And so there's another reason though, which I wanted to. Let me just draw what the product would be, right? So this product right here is going to be a little bit different than the product on the left side if we were to assign our arc groups. But actually that might make it a little bit too complicated in terms of rotation. Let's look at that later. Okay, so let's think about the base coming along and then the leaving group coming on the back side. So if the base comes on the left side in the syn-periplanar conformation, it's going to kind of be interacting with that leaving group. So the base is coming and the leaving group is going in the same general area, and so there's a lot of electron repulsion here. So there's high energy repulsion, so this is not likely and it's not easy to do, and so the syn-periplanar conformation is not ideal. Okay, so we prefer the anti-periplanar conformation because we have the base, the electron-rich base, and the electron-rich leaving group on opposite sides of one another as they come in or leave. Okay, and so there's not that repulsion that we get from syn-periplanar. This is really important because that does affect the stereochemistry of the products that are formed. Okay, so it's really important to look at them in that sense. So for example, if we have this particular compound and we have that carbon right there, specifically that one as an S or R conformation, leaving the other one as it is, we don't even care what it is, right? So let's put a C6H5, by the way, is a benzene ring, or a pH, you can call it a phenyl group. And then let's say we have, on the left side, we give it some wedges and dashes, and we got the benzene ring projected towards us. And then on the other molecule example, we have the same conformation on the right side, but we swap the conformation on the left side. So the wedge is no longer a benzene ring, it's a CH3, and we throw that benzene ring in the back. Okay, so what that gives us is, let's see, we got a S conformation on the left and then a R conformation on the compound on the right. Okay, so what we're going to see is how this alkene product is going to differ when we have these two different conformations, because the stereochemistry or the approach of this particular elimination reaction has to be anti-periplanar. That puts the hydrogen and the bromine in a fixed position, and also the other substituents in a fixed position. So when you're drawing the alkene product, it's important that you get the substituents on the correct side, right? So the wedges should be on the same side and the dashes should be on the same side. And so however you want to draw it, they're just on the same side, at least of the double bond. Okay. And so this is really important. We also have our two groups on the right the same, and then two groups on the left, you can see that they are swapped. So the benzene rings are trans to one another on the left, but they are cis on the compound on the right. And so they are different isomers. They are different stereoisomers, and they are diastereomers of one another. Okay, so they are non-superimposable mirror images. Okay. So the cool thing about this is the same thing goes for cyclohexane rings, and that's going to make this particular type of reaction really interesting, and we'll see that shortly. So let's say we got this chlorocyclohexane. I just drew a wedge on it, just so we can kind of get an idea. It doesn't matter. But let's draw our boat conformation. Or a chair conformation, sorry, and we have the chlorine in the equatorial position. We know that equilibrium occurs. We have a chair flip that puts our chlorine in the axial position, right? So let me move this over so I can get everything on the same page. My bad. There we go. So it goes back and forth, right? Now, when it comes to elimination reactions, however, the equatorial position does not allow for the antiperiplanar conformation. And so we still want the antiperiplanar conformation, and the only way we can achieve that is if our chlorine is in the axial position or our leaving group is in the axial position. And that gives us, at the adjacent carbons, the other axial hydrogens that are trans to it are going to be antiperiplanar to that. If the chlorine's in the equatorial position, the thing that is antiperiplanar to it is the adjacent carbon-carbon bond, and so that's not gonna help. That's not what we want. So this is exactly why we had the trans hydrogen and the chlorine on this particular one that resulted in the alkene product, because we had, let's say, a chlorine in the axial up position, we would have a hydrogen in the axial down position, and therefore the antiperiplanar position. And so this di-transaxial antiperiplanar orientation allows for the formation of the alkene. However, if we have this blue cyclohexane ring with the chlorine up, we have to have a hydrogen up, and that does not allow for the antiperiplanar conformation to occur, and therefore this reaction does not occur. And so that's exactly why this is really important to understand and to kind of make sure that we have the axial leaving group as well as the hydrogen, but they must be trans to one another. And so if we're aware of that, these reactions can be extremely easy, because we don't even need to draw the chair conformation out. We should understand why they need to be trans, but in order to determine the products, we don't need to look at that. So what are the major products of the E2 reaction for these two things? Okay, so let's see what we've got here. So we want to identify the alpha carbon as well as any beta hydrogens, right? So here's a beta hydrogen. We also have a beta hydrogen here and here. There's two of them on that one. So in that case, that side's free game. We can definitely form a alkene on that side, but what about the other side, right? So draw out all of your beta hydrogens and then go from there. You want to make sure that you can find a beta hydrogen that is trans to your leaving group, chlorine in this case. So since there's both trans on this compound on the left, then we're going to get two different alkenes at least, right? So, but for the other one on the right, we have a beta hydrogen that's trans on the left side or upper left, but not on the right side. So there's only one beta hydrogen that's trans, and therefore we're only going to get one product. And why is this so interesting and important to point out? Well, now that we know about stability of alkenes, we can see that at least on the second product, what we're going to get is the least substituted alkene. So let's draw these products out right here. Boom, boom, boom. Let's see. Yeah, that's right. So we have a tri-substituted, of which is the major product compared to the di-substituted. And then on the compound on the right, what we get is this alkene here. Now this is also a di-substituted alkene, but it is the major product because it is the only product. And how you like me now? Look at that. We're putting on a show right here. This is gorgeous. Oh my goodness, how did he make the least substituted alkene? Oh my goodness. Well, of course, we didn't have that anti-pair plane of conformation because this hydrogen, the beta hydrogen, wasn't trans to the leaving group. Okay? Anyway, so let's take a look at this guy right here. Remember that time when Chickenfoot doesn't like to be in the axial position because it's too sterically hindered, and we had 100% conformation of it in the equatorial position? Well, that actually comes into play here as well, because if we have a chlorine that is, let's see, if it's right next to it, it could be at a different position, but if it's a 1-2 substitution pattern and it is trans to it, then it can never be in the axial position because that would require the Chickenfoot, the tert-butyl group, to be in the axial position as well, and that's not allowed. We know the equilibrium does not exist, and it's 100% that compound on the left. It's 100% that bitch. Even when I'm crying crazy. You know what I'm saying? Like, why is the leaving group great till it's gotta be great? That's messed up. You know? Shout out to Lizzo. Check her out. Have fun with this. It's good stuff. Check it. Put in that practice, though.